What about the homework? Is it done?
No.
Are you done at least with problem number 3?
Yes.
Okay, I think we're going to have some time to talk about problem number 4 on Friday, okay? So, what?
Isn't it due?
It's due
Yeah,
on
it's
midnight.
due Friday, but it's due Friday, 11:59 p.m. Right? So we're gonna talk a little bit about on Friday at noon. But if you need some more help, remember you can talk to the TAs too. All right? It's exactly the same problem as 3, but just with a lot more data. Well, all right, guys. I forgot to say last time that we have finished now chapter 2. I strongly recommend that you go through the notes. It's not a lot to read. You'll see you'll finish it very quickly. There are a few more things in here that I might have not said in class. So please go through that, solve the problems in there. Those are going to help you to solve the homework too. And now we started last Monday on talking about stresses and continuum mechanics in 3 dimensions, and today we'll talk about elasticity. I know that you already know some about elasticity, but our objective now is to take linear elasticity to 3 dimensions, okay? So, let's get started with this. There is one more thing that we're missing about theory before we get to play here with this small load frame. We talked about stresses last time. Now we know that in 3 dimensions, we're going to have normal stresses, 3, and shear stresses, which are going to be 6 different stresses. And you're going to have the same on the other side of the cube, which are going to be the same. We said that we can write that stress tensor, this physical representation, into a matrix, and it looks like that, with normal stress on diagonal and shear stress on the off diagonal. And if you calculate the eigenvectors of that matrix, you're going to get what are called principal stresses. As long as your matrix has real numbers and it is symmetric, which is going to be the case of all real stress tensors, you're going to find eigenvalues which are also real numbers, and they are going to exist. If your matrix is not symmetric, sometimes you can get imaginary numbers, but that's not going to be the case here, okay? Because your matrix is going to be symmetric, it's going to have real numbers, and you're going to have real numbers as eigenvalues for principal stresses. And we said that those principal stresses are going to be aligned with what are called principal directions. In those principal directions, you only have normal stresses, you don't have any shear stresses. That's why they are called principal stresses. Okay, so we wrote then the matrix of effective stresses, and now we're going to talk about strains or deformation. When you apply stresses to a solid, as a result, you get a deformation of the solid, or also called a strain. I know that you're familiar also with strain, but now our job is to extend this concept to 3 dimensions, okay? And we're going to start with 2 dimensions, but then we're going to generalize this to 3 dimensions. So let's start with a solid in this coordinate system where 3 is pointing out of the whiteboard, and originally we have a cube that has a length in this direction, dx1. Let's say that we apply a tensile stress on this face. And because it's a solid that it is elastic, it's going to deform. As a result of that deformation, let's assume that it stretches and only that face moves and the other face doesn't move. This additional deformation, we're going to call it DU1, where U stands for displacement. Whenever we have this kind of deformation, we're going to call this type of deformation a linear strain, because the deformation is in the same direction of the applied stress. And in particular, in this case, we're going to call this deformation epsilon 1, 1. Why 1, 1? Because we apply stress in direction 1, the tensile stress, and we have a deformation also in direction 1. And how would you define that deformation? What is deformation? You guys remember the definition of deformation?
Change in length.
Change in length divided
By the original length?
the original length. So what would be the change in length in this case? The du1, what would be the original length? dx1, right? So this is going to be our definition of strain. I'm going to explain a bit why I use this d, but I can tell you in advance that it's related to a derivative, okay? Because we have to generalize this later on, and that's going to be a derivative. Okay, so that's in one dimension, or in direction 1 to be more specific. We can do the same thing in direction 2. Now, instead of stretching the solid in direction 1, we're going to stretch it in direction 2. And as a result, we're going to change the length. This is dx2. Notice that dx2 is aligned with direction 2. And du2 is also displacement in direction 2. This is going to be another linear strain, which is going to be du2 divided dx2. The same as before, but it's in the other direction. And similarly, if we do this in the third direction, we could get epsilon 3,3, which is going to be the change of length in direction 3 divided the original length in direction 3. All of these are called linear strains. And something very important about linear strains is that they do produce a change of volume. You see that the volume after deformation is bigger than the volume before deformation. So the volume change. It's not the same as before. And that's not going to be the same with the next type of deformation that we're going to do in this case. The axes are going to remain the same. Our original condition is going to be the same. But now I'm going to apply a shear stress instead of a tensile stress. I'm going to apply a shear stress which is more or less like this one, in which I apply a shear stress in this direction. And notice that in order to counteract the shear stress, that torque, I need to have one that goes like this. As a result, if I combine these two, this is pulls in this direction. If I combine those two, those pull in this other direction. And the form configuration of the solid will look something like what I'm drawing right now. Okay, so what kind of, we said this is a shear deformation now, but what we want to do now is to relate the changes of displacement to the change of length. So let's see, did the length in direction 1 change significantly? imagine that this is a very, very tiny change of angle. Do you think dx1 would change a lot? Not very likely, right? And dx2 also is not going to change a lot. But this point over here moved an amount in direction 2. And this point over here also moved an amount in direction 1. And if we take the tangent of the angle of distortion of this solid, the tangent of that angle is going to be, what is that going to be, guys? The tangent of this angle? du1 divided dx2. Notice that now these are crossed. And that's going to be the same angle as that angle over there, which is du2 dx1. And the shear strain is going to quantify that distortion angle, going from a right angle to something which is not a right angle anymore. And in order to do that, we're going to define this shear strain, which is going to go by epsilon 1, 2, as the average of these amounts. du1 divided dx2 plus du2 divided dx1. So this is just going to be that angle of distortion. That is what we're going to call a shear strain. And in a shear strain, there is no volume change. Why that? Because if I have very tiny deformations here, the volume is going to be still the same, not unlike these ones. And we can also generalize this distortion. In this case, we have distortion in the plane 1, 2, but we could also have distortion in the plane 2, 3, which is going to be this one over here, right? Or we could have a distortion in the plane 1, 3, which is going to move the solid like that. So we can write all of those shear strains in the other 3 dimensions, and with that, we will have all the strains that we are looking for. And now, how do we write this mathematically? Well, we use, similar to the case before, we use a matrix. And now this strain is going to go into a matrix, and we're going to call it a strain tensor. And similarly as before, in the diagonal terms, we're going to have the linear strains, which are related to normal stresses, epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3. And in the all diagonal terms, we're going to have the shear strains related to shear stresses, epsilon 1, 2, epsilon 1, 3, epsilon 2, 3, epsilon 2, 1, epsilon 3, 1, and epsilon 3, 2. And let me write now this as using the equations that we used before, the definitions. This is going to be equal to du1 divided dx2, du2 divided dx2, du3 divided dx3, and here I'm going to have 1/2 du1 dx2 and this one is going to be du1, notice dx3. Just one more. The other one is similar. It's exactly the same value, and it's going to be du3 dx3 plus du3 dx2. Okay. So this is going to be our strain tensor. The important thing here that you remember is that these deformations are linked to changes of displacement in space. And it's not the same as just displacement, because, for example, I could throw this eraser on the Earth, and it's displacing, it's rotating, but there are no stresses in it, because the distance between, say, this point and this point is always the same, right? Even if I throw it. When the solid does get strained is when there is a change of displacement related to the change of original length. As I throw this, if the displacement from here and here, they both change the same amount, and the original length remains the same, there is no strain. But if I compress this, and now there is a change of length, that's when I get strains. And it's the same with shear strains. Only when there is a change in angles between the original angles, we're going to have a shear strain. And that is what these derivatives are telling me, that changes of displacement divided the changes in the original position is what is going to give me strain. You have a question, Omar?
Should that be du1 over dx1 for the first term?
Where?
On the first term, because all the
The second matrix. Left half of second matrix.
dx.
Du1
No, very left, far left.
Far left.
Yep.
Oh, in that one?
Yeah.
Yes. Thank you very much. Okay. All right, so let's see now how we use this into what we know as linear elasticity. Basically, what we have one step here that we have to close in order to relate these two. Basically, we have stresses, and we'd like to relate those stresses to strains, right? Or let me put it differently. We know that if we apply a given stress